can deduce surprising stuff from the ocean's geochemical record, everything from the size of polar ice sheets to the aridity and vegetation on the continents. That's the point of today's video. We get at the size of ice sheets by estimating how much ocean water has evaporated, turned into snow, and accumulated as glacial ice. I mentioned last time that in oxygen isotopes, the lighter isotope, oxygen 16, also evaporates more easily than the more sluggish heavy isotope, oxygen 18. So when water evaporates, the resulting water vapor and the clouds they form are enriched in oxygen 16 compared to its abundance in seawater. When water vapor falls as rain or snow, the oxygen 18 is the first to preferentially be rained out, leaving the remaining vapor even more enriched in oxygen 16. Eventually, when the last rain or snow is precipitated, this moisture is very negative Delo 18. For example, Antarctic precipitation and glacial ice has an oxygen isotope ratio of, say, negative 50 per mil, compared to the 0 per mil seawater that ice was originally derived from as evaporated water. So the more ice there is on land with lots of oxygen 16 in it, the less of this isotope there is in the ocean. This is a classic reservoir effect, like I mentioned at the start of class. As polar ice sheets grow, oxygen 16 is extracted from the ocean, and the Delo 18 ratio of the remaining ocean water becomes increasingly positive. A neat result is that we can detect how much ice there is on Earth, based on the changes in the Delo 18 of seawater. Pretty clever. The Delo 18 of seawater changes from, say, 0 per mil today, where we just have, say, Antarctic ice sheets, to about +1 per mil when there is lots of ice on the northern continents as well. There are corresponding changes in the Delo 18 measured on foraminifera growing in that seawater, such that the Delo 18 of benthic foraminifera changes from, say, +2.5 per mil today to about +4 per mil in the peak of the last glacial period. Part of that isotopic change is due to differences in temperature, but a big part is related to the amount of ice created on the poles. Now, back in the Cretaceous, when there were no glaciers, the oxygen isotope ratio is very negative, because all that oxygen 16 that is locked up in modern ice was back in the ocean. One implication is that if there wasn't any glacial ice, then sea levels must have been much higher than they are now. Indeed, the middle of North America was flooded with the Western Interior Seaway that stretched from Texas all the way to the Arctic Ocean. And most of Western Europe was underwater too. These epicontinental seas become the sites of shallow water chalk deposits that include the famous White Cliffs of Dover in England. Cretaceous seas were higher than now, not just because there were no glaciers. Hot climate like that in the Cretaceous causes seawater literally to expand, which contributes to higher sea level back then. In addition, there was lots of seafloor spreading in the Cretaceous, and the connection to sea level is that this hot, buoyant, young crust displaces water onto the continents, also accounting for higher sea levels than today. Now, the long-term positive drift in the oxygen isotope ratio from 100 million years ago to the present is partly due to the growth of ice sheets. Growth was relatively steady at times, like in the Doubthouse period from 35 to 45 million years ago, as indicated by a steady increase in the Delo 18 ratio in benthic foraminifera. Other times there is rapid growth in polar ice, like at the base of the Oligocene 34 million years ago, or in the last 5 million years when the Arctic and northern continents became extensively glaciated. You can also see that variation in oxygen isotopes increases towards today. Glaciers can melt pretty quickly, so that ice sheets are not permanent things, but they expand and shrink over time with changing climate. So as more ice forms globally, there's also more melting during the intervening warm periods, and this accounts for the increasing variation in oxygen isotopes in the last 30 million years. Besides sea level and ice sheets, we can also deduce the changing amount of oxygen dissolved in the ocean. In the greenhouse world, the world's oceans were badly oxygenated because warm water holds less oxygen in solution than cold water does. Warm water also speeds up the physiological energy demands of everything from bacteria to whales. Organisms literally have faster metabolisms in warm conditions, so they need to eat more when it is warm than they would in a colder environment. As a result, bacteria in a warm ocean tend to completely oxidize available food, and this depletes the ocean of oxygen as well. A consequence is that the greenhouse ocean was not as well oxygenated as the modern ocean. The epicontinental seas, for instance, were prone to being driven into severe hypoxia. Indeed, the Jurassic and Cretaceous ocean records are punctuated by oceanic anoxic events, also called OAEs. These form when the ocean becomes extensively depleted in oxygen, and organic matter is buried abundantly on the seafloor. OAEs are represented by black or dark gray rocks, reflecting abundant buried organic matter. Oxygenation improves, as it turns out, in the icehouse world, as the oceans cool and these OAEs disappear. So far I've focused on the oceans, but what about the land? We can infer aspects of the terrestrial environment also from first principles. For instance, the hot greenhouse of the Cretaceous and the Eocene probably had very high humidity relative to today. The reason is that a warm ocean is easier to evaporate than a cold ocean, and warm air also holds more moisture than cold air does. Forest ecosystems are favored by having a wet atmosphere, so jungles do well in hot, humid climates like the Cretaceous greenhouse world. Forests amplify these effects on humidity since trees transpire water vapor as well as shading wet undergrowth and leaf litter. A wet atmosphere also favors plants that do not die back seasonally, so forest trees do well. So for all these reasons, a direct conclusion from the warm temperatures implied by the Cretaceous and Paleocene oxygen isotope record is that there must have been extensive forests on all the continents. However, as the oceans cool in the Oligocene and Miocene, all of these factors reverse. There is less evaporation off a colder ocean, the air is drier as well because it is cool. Forests give way to more arid plant communities like grasslands, which can dry out and stop growing in the dry season. So by first principles again, we can deduce that as oxygen isotopes become more positive, indicating a cooler ocean and poles, grasslands must have replaced forests in the more arid regions of the continental interiors. Indeed, grasslands do expand on all the continents starting 25 to 35 million years ago. We see this vegetation change in the fossil record of plant phytoliths. Many plants secrete opal in their structural tissues and leaves. As fossils, these phytoliths record the change in the plant community going from the greenhouse to the icehouse climate. Grasses appear in the phytolith fossil record in the late Cretaceous, say 90 million years ago, which amazingly enough is actually consistent with molecular clock estimates for the evolutionary appearance of the grasses. The first grasses were forest species such as bamboo. Even today, bamboo forms tree-sized plants in Japan, but is also abundant as knee-high understory plants in Southeast Asian forests. By the Oligocene-Miocene boundary, say 23 million years ago, there was a switch to the dominant occurrence of open grassland species and the loss of broadleaf forests and conifers. All the continents save Antarctica developed grasslands in the Oligocene or Miocene. Now, among grassland species of plants, there are trends towards more drought tolerance as the planet becomes increasingly cooler and more arid. One response to increasing aridity is the appearance of the C4 grasses 6 to 10 million years ago. These grasses handled drought much more efficiently than the previously dominant C3 grasses that thrived when the forests were first turned over to grasslands. The drive towards open grassland is paralleled by the spread of desert environments. Cacti, for example, appeared about 35 million years ago, roughly coincident with grassland expansion. But really iconic groups like the columnar cactus are much younger, appearing in the last 10 million years. Hence, aridification is an ongoing trend, particularly with the development of really extensive northern hemisphere glaciation in the last million years or so. Now, the type of terrestrial vegetation affects animals too. The extensive forests of the Cretaceous and Paleogene favored small animals that could easily move through the undergrowth. Forest animals are usually non-herding, often arboreal, and have low crown teeth for browsing, eating twigs and leaves and fruits and coarse vegetation. These include things like Hyracotherium, the first horse, that was the size of a house cat. Hyracotherium was probably a solitary browsing animal, somewhat like the living agoutis of tropical America. I've actually watched these agoutis feeding on figs dropped out of trees in a park in Panama City. They emerged at dusk from the jungle in ones and twos to see what the day's fruit production had provided. I confess it was not hard to imagine that the scene was back in the Eocene of Wyoming, with the forest hung heavy in vines, where it would be a huge advantage to be the size of an agouti to make your way through the tangle. Now, grasslands, in contrast, favor bigger, swifter animals. On the open plains, herds can detect predators much better than solitary animals. Speed also becomes a factor in both escape and being a predator. Big bodies have endurance for long-distance migration as well. Further, the phytoliths in grasses are very abrasive, so animals eating grass need high-crowned teeth that can take a lot of wear. Therefore, the development of grasslands drives major radiations of antelope and horses, both of which become bigger-bodied, swift, often herding, and with high-crowned teeth. So, in summary, we can get quite far in understanding the evolution of Cretaceous and Cenozoic ecosystems just from the oxygen isotope record. It's remarkable that one set of measurements provides such a finely textured history of our world. We get temperature, sea level, ocean oxygenation, drought, and the vegetation change, all from that one proxy. We are also fortunate that there are long, fairly continuous records of oxygen isotopes in deep sea sediments, which have the advantages that the record is quite continuous and is generally well dated thanks to a whole host of methods, from biostratigraphy, like I've done in the past, to astrochronologies. There's still much detail to be discovered here. This is for you to think about. A frontier area, for example, is linking the generally shorter, more discontinuous, and poorly dated terrestrial records from things like lakes and speleothems to this marine record. There is yet much to be done.